CS50X itself, but we welcome your questions and comments in the chat along the way. And in fact, if any come up, my colleague Colton will be in back to relay some of them as needed to me. In the meantime, this course will not go live on edX and elsewhere until later this year, along with the new and improved assignments. So stay tuned for more. And thank you for joining us. Our next live stream after this afternoon here in Massachusetts, United States, will be tomorrow morning with CS50's own Colton Ogden. Check out cs50.ly/Zoom for that URL. OK. This is an introduction. Hello, world. Hello, world. My name is David Malan. For business. Oh, but I guess. Hello, world. My name is David Malan, and this is an introduction to computer science for business, for law, for medicine, really for anyone working in the real world who wants to better understand this increasingly technological world of ours, and ultimately, and dare say most importantly, be able to make more informed, better decisions as it relates to technology. Now, computer science itself is all about information. Indeed, the focus of today's lecture is going to be on interpreting information. And even if you're not a computer person per se, odds are at some point, you've heard that computers really only speak a certain language, zeros and ones, the so-called binary system, bi implying two, because they only have two letters in their alphabet, the 0 and the 1. Now, by the end of today's lecture, you yourself will be able to speak and read binary, if a little slowly and with some practice. But the hope there is to take the first of the layers off of this field of computer science so you better understand what so permeates today's society, today's tools, today's technology. Now, what really is computer science beyond information? Well, it's really the study of that information. How do you represent it? How do you process it? And with computer science, of course, there's this association with code, programming, that so many of you know of, if not have a bit of experience with yourself. But in this course, we'll focus far more than on code and on first principles instead, underlying germs of ideas that underlie today's technologies, today's code, today's systems, and more, so that ultimately, after this class, you can not only better understand the technology you're using, but for instance, if something goes wrong, you can much more effectively deduce through logic and reason what might explain that issue, and of course, how you can then solve that problem. Because at the end of the day, too, computer science really is about solving problems, sometimes with code, sometimes with paper pencil, sometimes with other techniques as well. Now, code is really the translation of a lot of the ideas we'll focus on in this course to a language that a computer can understand. And a lot of computer scientists certainly write a lot of code, but increasingly, we're entering this world of sort of no code, so to speak, whereby you can still tell a computer what to do, but you might use so-called natural language, your own English words, your own spoken words in any human language, because someone else has written code to understand that human language and to convert it into, eventually, those underlying zeros and ones. And so we'll really focus at all different layers of complexity in this course, not only the zeros and ones, which frankly we'll quickly leave behind us, but we'll also quickly abstract on top of those zeros and ones and solve problems at a much higher level. Indeed, among the takeaways of computer science as a field, this course in particular is to equip you with techniques, namely abstraction being among them, via which you can solve problems in the real world and take a step back at what seems to be a very large problem, perhaps decompose it into smaller problems, but at different levels of complexity, such that sometimes you might need to drop down to a fairly low-level implementation detail to implement something, to solve something, but often we can reason about problems at a much higher level instead. So let's go. Screwed up already. Not supposed to reveal this picture. So if you're playing along at home, let's pick this up. Why don't I start here, and I'll go back to this, the lectern so that I can then talk about this picture. All right. In fact, if you will, let's go ahead and play a little game. Odds are right now you're watching this online, but hopefully within reach you have a sheet of paper, maybe a ruled paper or printer paper or just scrap paper. So if you could, reach for a sheet of paper and a pen or pencil and see if I can't program you as our first exercise together to draw something on that sheet of paper. And among the goals here, beyond drawing a pretty picture that you can put on the fridge later today, is to ultimately think about how we might approach problems at a high level or at a low level. So in fact, what I'm going to propose first, assuming you've now gotten that sheet of paper, and if not, you can certainly pause and then come back. But assuming you have that piece of paper now and a pen or pencil, go ahead now and draw a circle on that sheet of paper. Below that circle, go ahead and draw a square on that sheet of paper. And then lastly, on that sheet of paper, draw a triangle. Fairly straightforward, not all that difficult, but I dare say because I presented to you those instructions at a fairly high level, and even if you know what a circle and a square and a triangle are sort of intuitively, you might not necessarily have drawn this very picture. Now, if you did, great. You're on track already, but there's many different ways you could have interpreted what I proposed. Like maybe you started with the circle in the middle of the page, a reasonable starting point. I probably should have clarified where I wanted you to start, maybe more to the top so you could actually fit everything. I probably should have clarified that the square is touching the circle, not just below it, and similarly that the triangle is touching the square below that. And even then, I probably should have clarified that the tip of the triangle is touching the square, not the base of the triangle. So even with these three simple shapes, because I spoke at such a high level of abstraction, just talking to you in terms of circles and squares and triangles, there's a lot of ambiguity and therefore imprecision. And the funny thing is about computer science and in turn programming, when you try to apply those ideas to a language that a computer understands, you ideally need to be as precise as possible so that there's no ambiguity, so that the machine ultimately does what it is you want it to do. Well, let's go ahead and try one more now. Let's go ahead and do the following, if you will. On the other side of that sheet of paper, or on some other piece of paper, again, pause if you need to go grab another, but using that same pen or pencil, go ahead now and do this. Put the point of your pen or pencil near the top middle of the page, and then draw a diagonal line down to the southwest, if you will. Think to yourself for a moment, which way is west, which way is east? So you do this right. But starting from that middle point near the top of the page, go ahead and draw a straight angled line to the southwest. Then, from that point, draw a similar length line straight down south. And then draw another line to the southeast, such that the end of that line perfectly lines up from where you first began. Then, from that point, which is probably near the bottom of your sheet of paper right now, draw a line straight up that's the same length as before. It's not going to touch that first original point accordingly. And then, from the end of that line, draw another line to the northwest so that you intersect the second point that you made with your pen or pencil. Now, go ahead and pick up your pen and pencil, put it back on the very first dot at the top middle of your sheet of paper, and draw to the southeast this time yet another straight angled line that's the same length as all the others. Then draw a straight line down to the south. That's the same length. Then draw another angled straight line to the southwest, which should ideally intersect that bottommost point that you drew earlier. Now you can either trace the line vertically above that to the north, or you can just pick up your pen or pencil and put it on the point that's immediately above the one you just led to. And lastly, draw a final straight angled line to the northeast so that you intersect the second point that you made this time around after picking up your pen or pencil for the second time, or for that one and only time. All right. Now, if you got this picture completely wrong, fine, it's on me. But wouldn't it have been nice if I just told you to draw a cube on the sheet of paper, therefore giving you an abstraction that's many layers above the low-level detail that I just dragged you through verbally by giving you directions, north, south, east, west, and diagonals therein. I could have just told you to draw a cube, abstracting away all of those lower-level implementation details. Of course, if I asked you to just draw a cube, you might draw this. Some of you, indeed, might very well have. But your positioning of the cube might not have been the same. You might have rotated it somewhat. You might have drawn lines in such a way that the aspect ratio isn't quite the same. So your cube could have ended up very different from mine, even if you were following my directions as stated, draw a cube. But we need more detail. We need more precision and therefore less ambiguity. So these two simple pictures, the circle, the square, and the triangle vis-a-vis this cube, sort of alone give us an opportunity to talk about abstraction, talking at a fairly high level. But with that comes not only understanding, but potential misunderstanding. At a lower level, though, you might have greater understanding, because if you just follow the step-by-step instructions, I mean, how really can you go wrong? But you start to lose sight of the forest for the trees, so to speak, whereby it's not at all obvious what you're drawing until maybe the final stroke of the pen or pencil, at which point, oh, it was a cube. Why didn't he just tell me a cube the whole time? So among the things we'll do in this course, in computer science more broadly, is get you more comfortable thinking at different levels of abstraction, high level, low level, and everything in between. And indeed, when the world's software developers set out to implement some new tool, some new product, what they're often doing first is sort of verbalizing what it is they want to build as that product, maybe rattling off the feature list. But it's only later that they go lower level and start talking about the implementation details. Step by step, how are they going to achieve that very task? And indeed, increasingly nowadays, thankfully, we have techniques like AI where we can talk to the AI, again, at that higher level abstraction, and ideally, it will output those lower level details. But even with our pictorial design here, and you are all actually intelligent, not artificially intelligent, even then there's going to be potential ambiguities and room for error. And that really speaks to what we can and can't do, perhaps, with AI, at least when it comes to verbalizing our instructions thus far. So without further ado, let's start to solve some problems. And in fact, let's give you a pictorial mental model via which to approach really any problem in general. This picture, in fact, is perhaps the simplest way to describe computer science and, in turn, problem solving. Any problem in the world, by definition, has some input, like the actual problem you want to solve. The whole point of problem solving is to solve that problem, and that, therefore, we'll call the output. And the secret sauce in the middle, the proverbial black box, is where all of the interesting hard work gets done. The step-by-step process that takes that input and turns it into output. And this is true really of any piece of software, any problem in life. You could simplify it into this mental model. And so even if some of the topics in this course become a little more complex, feels a little more sophisticated, rest assured that we could map it to this relatively simple model here. So I think, though, we need to agree first on how we're going to represent those inputs and outputs. And the spoiler, of course, from the top of the hour is that we are just going to use binary, ultimately zeros and ones. Well, why is that? Well, let's first rewind one step further from binary to unary, which is an even simpler system, a mechanism for representing information. In fact, the simplest way I could count, maybe the people in this room here, would be 1, 2, 3, 4, 5, simply using my fingers, my digits, if you will, to count the number of people in the room. That's unary notation because each of my fingers in this model represents one person in the room. More mathematically, unary is also called base 1 because you only have one symbol in your alphabet, one digit, if you will. A finger and a finger and a finger and a finger. However many fingers you have is how high you can count in that system. But of course, we know we're already headed into a world where computers use not unary, but binary. And so in fact, mathematically, the base system we're about to talk about is actually base 2. And indeed, instead of just having fingers at their disposal, computers actually have zeros and ones by convention, otherwise known, of course, as binary. Now, there's probably another term you've maybe heard of over time, maybe not binary digit, but a binary digit is just literally 0 or 1. You've probably heard a simplified version of that phrase, bit, which is binary digit for short. A bit is just literally a 0 or 1. So what computers are really storing inside their memory somehow is a whole bunch of zeros and ones, aka bits. They're storing these bits to represent information. Now, what is a bit? It might be a 0. How does a computer store a 0? Well, in any number of ways, but at the end of the day, how do these devices work? Well, I go home with my laptop or phone. At some point, I have to charge it or plug it into the wall in order to use it. That's because there's going to be, therefore, some flow of electrons that we could maybe capture or hold on to. And in fact, maybe the simplest way to store information in binary using zeros and ones is just to leverage that very electricity. So for instance, if there's no electricity and I'm not holding on to any of that electrical current, well, maybe we can just say, well, that's how we represent a 0. We don't hang on to any electricity at all. As a result, if we were to connect this device to like a light bulb, the light bulb would stay off in that scenario. So you might say in the physical world, you could use one light bulb to represent a 0 by just keeping it off with a switch or otherwise. Meanwhile, though, if we want to store some piece of information besides a 0, like a 1, well, why don't we just grab some of that electricity, let it flow, and hang on to it? So in order to represent a 1, we can use the metaphor of a light bulb that is on by switching it on. So in short, just by toggling switches in a device that's connected to some source of electricity, we can represent a 0 or 1 just by turning that thing off or on. In fact, in this room, I could turn all of the lights off and just claim, now this room is representing a 0. Or if I turn all of the lights back on, now this room is representing a 1. It's not the best use of space, but maybe we could use multiple switches and not just one main switch in order to count more higher than just 0 to 1. And in fact, I think that's what we might try to do here. Suppose that we have not just a single light bulb and in turn switch, or if you prefer, a single bit, a single 0 or 1. What if we have 3 of them at here? Let me fix that, sorry. In fact, let's go ahead and do that. Suppose that we want to count higher than 1. Well, I do think we're going to need more light bulbs. We're going to need more switches. We're going to need more bits, 0s and 1s. So suppose I give us as many as 3. Now, it would seem that I could still represent the number 0 by just leaving all 3 of these light bulbs off. But if I want to represent now the number 1, I could very reasonably just turn on one of those light bulbs. If I want to represent the number 2, well, I go ahead and flip the switch and turn on 2 of those light bulbs. And if I want to count to 3, I could just turn on a third switch and turn on the third of those light bulbs. Now, this is great because I can count higher, but this isn't really the most scalable system for representing information, because if I want to count to 4, I need a 4th bit. If I want to count to 5, I need a 5th bit. 6, a 6th bit, and so forth. That doesn't feel very efficient. And in fact, when I look at this screen here, having studied computer science in the past, I can actually claim that I can count, even with 3 light bulbs, much higher than 3 alone. In fact, I could count as high as, I'll claim 7, 0, 1, 2, 3, 4, 5, 6, 7, using these exact same 3 light bulbs. But I think what I need to do is not just turn them on in any order and count the total number of bulbs on. I need to permute them in some way. Take into account, that is, which of the light bulbs is on and when. So what do I mean by that? Well, let's start over. Let's turn all of the light bulbs off, and I'll claim again that in this scenario, we are now representing the number you and I know as 0. Now, if I turn on one light bulb, I'll claim that this is how a computer would represent 1. Fairly intuitive and no different from what I've done before. Let me go ahead and claim that I could turn on this light bulb, but now I'm going to claim that this is the number 2, even though only one light bulb is on. Well, let me turn on a second light bulb. Now I'm going to claim that this is how a computer would represent 3. Not 2. Let me go ahead and turn on this and only this light bulb and claim this is how a computer would represent 4. 5, 6, and here now is 7. So I can represent, in fact, a total of 8 different numbers, 0, 1, 2, 3, 4, 5, 6, 7, simply by using these 3 light bulbs. Now, how in the world did I come up with those patterns? Well, you and I are familiar with actually a similar system, even though we probably don't think about it day to day in the form of light bulbs. You and I actually use every day base 10, where you actually have 10 digits in your vocabulary, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so much higher, of course, than just 0 or 1. And there's 10 of those total, 0 through 9. That, of course, is the so-called decimal system, dec implying 10, because, again, you have 0 through 9 at your disposal. Well, how do we represent numbers in our normal everyday lives using the decimal system? Well, let me put forth 3 digits on the screen here. Here are 3 digits, 3 symbols, 1, 2, 3. But all of us, at glancing at these, probably immediately think to ourselves, well, 123. It's just completely intuitive after all these years of schooling. But why is this pattern of 3 symbols, left to right, 1, 2, 3, actually representing information like 123? Well, all of us, even though we probably don't think about numbers in this way since grade school, know or recall that this rightmost column is generally known as the ones place, or the ones column, the tens place, the hundreds place. And therefore, the position of each of these symbols implies some sort of magnitude, because this is 100 times 1, this is 10 times 2, this is 1 times 3, which gives me now, of course, 100 plus 20 plus 3. Oh, that's why we get back to 123. And that's why we don't say 1, 2, 3. We say 123 because the positions of each of these symbols means a little something to us. All right, so that's hopefully quite familiar, whether you use 1, 2, 3, 4, 5, 6, or any other set of digits. But how, though, is a computer getting away with just zeros and ones and no 2s, 3s, 4s, 5s, 6s, 7s, 8s, or 9s? Well, it turns out it uses a very similar approach, ever so slightly tweaked. So here's just some generic placeholders for 3 digits per the number signs here in the ones column, the tens column, and the hundreds column here. That, though, notice mathematically, just so happens to work out to be 10 to the 0th power, 10 to the 1, 10 to the 2. OK, and notice the 10 now. We're in the decimal system still, dec implying 10. So the base here is indeed base 10, but the exponent varies by the position or column that you're in. Meanwhile, the binary system, bi implying 2, because it only uses zeros and ones, simply has a different base, thus base 2. But those exponents are the same. 2 to the 0, 2 to the 1, 2 to the 2. If you do out that math, you, of course, get 1's column, 2's column, and 4's column. Meanwhile, I could keep going. I could get the 8's column, 16's, 32, 64, 128. And I could go on ad infinitum. But we'll keep it simple now with just these 3 placeholders for now. So this then, 0, 0, 0, or off, 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 if you will, is how a computer would represent the number you and I know as 0. Meanwhile, if I go ahead and turn on one of these light bulbs, which, heck, why don't I go ahead and do for real? Here I have 1 light bulb. Here I have 2 more. Let me go ahead and start with them all off as we have on the screen here. Here now are 3 physical objects that are representing the number you and I know as 0. How do I represent the number 1? Well, I dare say all I have to do is flip on one of these light bulbs, as by flipping a switch, holding on to a bit of electricity, and voila, now I'm storing 0, 0, 1. From your left to your right, 0, 0, 1. Now the 1, of course, the light bulb that's on, is in the 1's place. So if we do out the math, 4 times 0 plus 2 times 0 plus 1 times 1 gives us the number you and I know as 1. How about now? What pattern should I use to represent the number 2? I don't want to just turn on this light bulb here. I want to, in fact, turn off this light bulb here because I'm using base 2. Now I have, equivalently, a 1 only in the middle column. So I have 4 times 0 plus 2 times 1 plus 1 times 0. Of course, that gives me 2. So this pattern of light bulbs, this pattern of bits, zeros and ones, if you will, represents the number you and I know as 2. And we can continue to do this either by flipping light switches or pictorially here, 0, 1, 1, which is indeed pronounced, on rare occasion when you have to pronounce binary, 0, 1, 1, and not 11, as we would in our human world. This is 4 times 0 plus 2 times 1 plus 1 times 1, which gives me 3. This, meanwhile, is 4. This, meanwhile, is 5. This, meanwhile, is 6. And then lastly, how do I represent 7? Well, in that case, all 3 light bulbs would be on. All 3 bits would be all 3 bits would be 1, in which case 4 times 1 plus 2 times 1 plus 1 times 1, aha, that's where I get the 7. So in this case, simply by using 3 light bulbs or 3 bits, simply by turning them on in some order, therefore representing some pattern, I can represent any number of numbers at least up to a certain point. And then the certain point, when you're using just 3 bits here, is 8 possibilities. For the mathematically curious, that happens to be 2 to the 3rd power. But I can't represent with just 3 bits the number 8. I can only represent 8 total patterns, the largest one being 7 if I start counting from 0. But how could I represent the number 8? Well, if I kept drawing on the board here, I'd have eventually an 8's place. And in fact, if I give myself another bit, a little bit more hardware, more light bulb, more switch, I can, in fact, count to the number 8. Now, as a curious side effect, if you don't have 4 bits at your disposal, and maybe this is a really old computer that could only store 3 bits worth of information, you might actually accidentally, when counting from 0 to 8, wrap back around to 0, because if you don't have that 3rd bit and it's supposed to be there, you might actually confuse what you're storing in the computer's memory by just storing those last 3 bits instead. And we've seen this multiple times over the years. More on this down the line in this course and beyond. The Y2K problem, for those familiar. There's another one on the horizon in the year 2038. But more on that, I think, another time. Now, it is not...
David, can we stop you here?
Sure.
We'll pause. I want to replace your mic element real quick.
Sure. We'll take a short break and be back.
2.
Now, having just 3 bits is not all that useful. And in fact, it tends to be more useful to use bits in increments of 8. And in fact, if you've ever heard the phrase byte, perhaps in the context of kilobyte, megabyte, gigabyte, even terabyte, you're actually referring to units of 8 bits. So 1 byte is 8 bits. Now, among the upsides of talking in terms of bytes instead of bits alone is that we can solve another problem, in fact, already. For instance, here are 8 bits, all 0, and I've included for now the column values just so that if you're so inclined, you can do a bit of quick math. Now, nicely enough, 0, 0, 0, 0, 0, 0, 0, 0 represents the number you and I know in the real world as 0, because no matter how many of those columns you multiply out, you're still going to end up with 0. Meanwhile, if we flip all of those bits to 1s, as by turning on 8 light bulbs, then that's going to be a little more complicated math. In fact, just as an intellectual exercise, does anyone want to conjecture just how high you can count using 8 bits once you flip them all to 1, like this? I mean, you don't have to just kind of guess. You could do the math, like 128 times 1 plus 64 times 1 plus 32 times 1. Well, if you do out the math, you're going to get, spoiler, 255. Now, why is that? Well, you could actually cheat a little bit and do 2 to the 8th power, similar to how I proposed we do 2 to the 3rd power earlier, which gave us 8 possibilities. If you do 2 to the 8th power, that gives you 256 possibilities. But again, as before, if we start counting from 0, then we can only count as high as, in this case, 255. Now, in this course, and really in computer science in general, we're not going to dwell on arithmetic like this. These numbers are useful only insofar as they tend to occur a lot in different contexts, in different areas of computer science, as well as technology more generally. So for now, know that increments of bytes tend to be quite useful. So in fact, let's consider how we might solve a problem beyond numbers alone. How might a computer represent information like letters of the alphabet, say the English alphabet, for the sake of discussion? Well, at the end of the day, all a computer has is 0s and 1s, whether implemented in light bulbs like these here, or maybe, more realistically, using tiny little switches known as transistors. In fact, today's computers have millions of transistors, which means they can store millions of bits, and in turn, lots of bytes underneath the hood, so to speak. But that only would seem thus far to give us the ability to express numbers by just permuting those bits on and off and counting from 0 to 1 to 2 to 3 on all the way up to 255 or even beyond. But if that's all we have at our disposal, it turns out this is where I dare say computer science actually starts to feel maybe more accessible, maybe a little simpler than you might have thought. Because at the end of the day, if all you have is this vocabulary of numbers, well, that's going to be the solution to like every problem. In fact, why don't we just agree to represent the letter A in English with, who knows, some pattern of 0s and 1s that if you do out the math represents, say, this pattern here, 0, 1, 0, 0, 0, 0, 0, 1. Why? Well, we'll see why in just a moment. But this pattern of 8 bits, that is 1 byte, could represent, if we want, the letter A in uppercase. Now, what is this number? We can do some quicker math now. 128 times 0. I don't need to do the multiplication of the zeros, in fact. 64 times 1 plus 1 times 1 gives me, of course, 65. And this is indeed how, decades ago, a bunch of humans sitting in a room essentially decided to represent the capital letter A in English using the decimal number 65, or equivalently, the pattern of 8, or technically 7 early on, but nowadays 8 bits that ultimately gives you the number 65. Now, thankfully, they did something pretty reasonable and decided that, you know what, let's go ahead and represent the letter B in uppercase as 66, the letter C as 67. And in fact, they came up with a whole system known as ASCII, the American Standard Code for Information Interchange, which is a mouthful to say, but really just represents a mapping of numbers to letters, 65 to A, 66 to B, 67 to C, and so forth. In fact, here is a whole ASCII chart, if you will, of the original mapping. And if we focus on maybe the middle column over here, sure enough, 65 is A, 66 is B, 67 is C, 72 is H, 73 is I, and then there's a bunch of others as well for punctuation and other symbols, as well as some weird things that are really control characters, so to speak, that the computer understands, even if we humans, most of us, don't need to know or worry about those. So let's try a little exercise here. Here is a pattern of 3 bytes on the screen, each of which, if we did out the math, could be said to represent a specific number in decimal. For instance, if I do out the math, and I sort of do it mentally, and I kind of know where this is going, but I could do out the math here. This is the 128's place, the 64's place, the 32's place, and so forth. You too could do out the math. I dare say that this pattern of 3 bytes, or in this case 24 total bits, is going to give me the decimal number 72, 73, and 33. Hopefully that lines up with whatever mental math or paper pencil math you were about to do, because now the question is, if you indeed receive a text message, an email, a letter, using this encoding somehow, some pattern of zeros and ones that got that text message or email or document to you, what was the message you received? It would seem to be a 3-letter message, or 3-character message more generally. And let's take a look at that cheat sheet. Well, I got 72, so that's H. I got a 73, so that's I. OK, I think I know where this is going. HI, but what's the 3rd character? Well, we got to look to the left here. This is a very excited hi. HI exclamation point in all caps is indeed what message I seem to have received. So indeed, literally, right now, if you text your best friend or family member, hi, HI exclamation point, your phone somehow is sending 72, 73, 33 as some pattern that we just saw of zeros and ones, wirelessly or otherwise, to the recipient's device. And because your device and their device supports ASCII, this original mapping from letters to numbers, they see the exact same message that you have sent on your end. Now, of course, this only gives us the ability to express so many characters, the H's, the I's. There's a bit of an English bias, certainly in the American Standard Code for Information Interchange. And it turns out that 8 bits, or 1 byte, and technically early on only 7 bits, was not really nearly enough possible patterns to represent all human languages in the world. Indeed, I can think of accented characters, various Asian characters that you just don't have enough room to represent if you only give me 7 or 8 bits total to permute in some way. In fact, 256 total possibilities is not that high for all of the human languages in the world. So I dare say if we want to represent not just what you'd see on a US English keyboard, but accented characters like these, or heck, emoji like these that are omnipresent nowadays, we're going to need more patterns of zeros and ones than just 256 total, more than single bytes, and frankly, more than ASCII was designed to support. And so thus was born a different mapping known as Unicode, where a different group of people got into a room and decided ASCII is no longer sufficient because we have all of these other humans in the world who would like to be able to communicate digitally as well. I think we're going to need to build upon the ASCII system and make what turned out to be Unicode a superset thereof. So it turns out in the world of Unicode, at the end of the day, it's still just a mapping of numbers to letters, but using more bits as needed. In fact, in Unicode, rather than only use, say, 8 bits per character, you might instead use 16 bits for some characters. You might use 24 bits. You might use as many as 32 bits for some characters, which gives you many, many, many more possible patterns of zeros and ones. Now, thankfully, the folks who designed Unicode did indeed make it a superset of ASCII so that A is still 65, B is still 66, and so forth. Now, though, we just have more bits at our disposal to represent even more characters. So for instance, as a fun at-home exercise, does anyone want to guess in their mind what this pattern of zeros and ones is trying to say? It's quite a few zeros and ones. There's no gaps in between them, so this isn't 3 or 4 different characters. This now is one big character, if you will. I'll save us some time and do out the math. If you were to multiply all of the column placeholders by the zeros and ones in there, you'd actually get 4,036,991,106. Now, what the heck is that when we started counting originally at 65? Well, it turns out that this is the pattern of zeros and ones, and in turn number, that a bunch of humans decided shall represent a face. Damn it. How do I fix this? Now, what does this number represent? Well, this is the number that a bunch of humans decided shall represent a face with tears of joy. And in fact, what we know as emojis, which are certainly pictures on the screen, are technically characters. Even though we see them as pictures, we're seeing this picture, for instance, on an iPhone or a Mac because Apple has designed their software in such a way that when they see that pattern of zeros and ones, they show you this picture. By contrast, if you send that same message to someone who has an Android device, for instance, well, Google, the designers of Android, have decided to represent a face with tears of joy ever so slightly differently. So whereas this is the iOS and macOS version in that world, this is the Google version instead. And some companies nowadays have decided to take a bit of liberty when it comes to interpreting what the formal definitions are of some of these Unicode characters, for emoji in particular, such that on Telegram, for instance, you might actually get an animated face with tears of joy. But what's being sent to you in that text message, for instance, is just that pattern of zeros and ones, and the display of it is actually up to the recipient. And so as an aside, this has actually caused potential problems over the years because if two different companies, two different organizations interpret the definition of these emoji characters differently, well, it might not only just look different, it might convey a different meaning. In fact, years ago, it was decided by one company, then more, and then more, to change the implementation of the pistol emoji from being a proper gun to a water pistol instead. And you can imagine the dichotomy between sender and recipient. If they're on different platforms interpreting that same pattern of zeros and ones differently, the image itself might not actually appear the same. And there's other examples of this since. There will certainly be more examples of this in time. But emoji and Unicode more broadly are particularly striking insofar as the aspiration of Unicode itself as an organization, a consortium, is to be able to represent digitally all current, past, and future human languages. And indeed, these emoji, playfully as they might seem at a glance, are a wonderfully interesting way of transcending specific human languages and representing people, places, things, emotions in a way that doesn't require even understanding one particular human language as well. Well, as he continues to laugh at me here, let's move on to now how else we might solve another problem. At this point in time, we've been able to represent zeros and ones with our light bulbs or switches. We've been able to transition from there to representing letters of the alphabet. And so how now might we solve yet another problem? And that is, how do you know if you're, do I want to do that? Let me fix that one here. OK. Let's transition to now, still laughing at me. I was over here. Let's transition now to solving another problem with these same zeros and ones when it comes to images and pictures and colors. Because thus far, we've seen how we can represent zeros and ones using those bits, using those light bulbs, using those switches. If we abstract on top of those zeros and ones, we can just agree on a system like ASCII or more recently Unicode that allows us to interpret those same patterns of zeros and ones not as numbers per se, but as letters of an alphabet, be it English or something else. Well, what if we want to paint a picture with a computer and store an image, whether it's a GIF or PNG or JPEG or other graphical format with which you might be familiar? Well, we need to decide, using these same zeros and ones, how to store every color of the rainbow, if you will, so that the computer can store that pattern in its memory to represent some colors. And in fact, one of the most common ways for storing colors inside of a computer, like some of the yellow that composes that there emoji, is something called RGB, red, green, blue. Because it turns out we can, in fact, represent every color of the rainbow by mixing together a bit of red, a bit of green, a bit of blue in different amounts. And that can give me everything from black to white and every color in between. Now, how might this work? Well, suppose that we wanted to watch a movie back when I was growing up in a classroom. You might actually have sat behind or in front of this here type of projector. In fact, all these years later, I can still remember in a classroom in grade school sort of leaning up against the projector, feeling the warmth of the air coming out of it, because this was a behemoth of a device that was projecting some amount of red, some amount of green, and some amount of blue color onto the screen. And so long as those lenses were perfectly aligned so that every one of those circles lines up perfectly on the wall or projector screen, you would see a TV show or movie, whatever it was the teacher was displaying, by mixing together in appropriate quantities some amount of red, green, and blue in turn. Well, it turns out this is very commonly how computers, too, represent information digitally nowadays, even if they're not projecting it out with something as old school as this. In fact, if we were to take those same three numbers as before, 72, 73, and 33, which recall were bytes worth of information, 8 bits, so 24 in total, we could instead interpret them not as numbers, not even as letters, like HI exclamation point. We could reinterpret those 3 bytes as simply representing some amount of red, some amount of green, some amount of blue. Now, how much of each of those? Well, if each of these values is represented with a byte, or 8 bits, and 2 to the 8th power, I said, is 256, which means we can count from 0 to 255, it would seem that like 72 is kind of in the middle of that range, 73 is kind of in the middle of that range, 33 is toward the lower end of that range. So I feel like this is a medium amount of red, medium amount of green, and a little bit of blue mixed together. So if I indeed try to view these bits using not a calculator, not a text messaging program, but Photoshop or some graphical program, you know what? I'm going to see combined into one dot on the screen this amount of red, this amount of green, this amount of blue, such that if you combine those all together, in this particular case, I'm going to get a single dot on the screen that is roughly this shade of yellow. And in fact, you've probably seen at some point, be it on your phone or computer screen or even TV, tiny, tiny little dots called pixels. And each of those pixels or dots takes on a specific color. And whenever you see an image of a photograph, a TV show, a film on the screen, what you're seeing are thousands, if not millions, of tiny little dots, each taking on a certain color, maybe for a split second, which is painting that picture on the screen. In fact, later today, if you'd like, you can try looking up close at your phone or some other device, and you may very well see the tiny little dots or squares that compose that screen. Nowadays, in fairness, hardware is getting so good and so advanced and so expensive that those dots are so darn close together, it's increasingly hard to see them. But they are, in fact, there. So in fact, when we consider an image like this emoji, which again, underneath the hood is just a pattern of bits, zeros and ones, that Google and Apple and others are displaying to you pictorially because they support Unicode, that mapping from numbers to characters. Well, let's zoom in on this. Let's zoom on this once more. And in fact, if you do this in most any program that supports graphics, you'll eventually see the dots on the screen because I've zoomed in this case, which is to say that every one of these dots, be it a solid yellow or a closer shade of orange or brown here, is storing, or rather is being represented as a color using typically 3 bytes. Some amount of red, some amount of green, some amount of blue. So using 24 bits per dot. In fact, what people describe this as, therefore, is 24-bit color. And using 24 bits, you can actually represent millions of different colors for each of these bits, which gives you much more precision and much finer control over the colors. Now, I keep saying bits. Of course, each of these 3 bytes now is 24 bits. And of course, if you've ever downloaded a file, taken a photograph, uploaded an image, you probably know that nowadays we typically calculate the size of image in megabytes and the size of videos in gigabytes. Well, that just speaks to how many millions or even billions of bytes and in turn bits compose the image or the movie that you're in fact looking at. So this image might very well have megabytes in total of pixels and in turn color information just to store something like a smiley face, or in the real world maybe something like a photograph from outdoors. Now, how do you represent a video? Well, if you think back also to your childhood, and at least mine, you might recall flip books like these. And these flip books were tiny little books that you used your thumbs to sort of flip through the pages pretty quickly, like 1 page per second or even faster than that. And because your eyes were seeing a whole bunch of pictures quickly, it was creating the illusion of motion. And in fact, the picture book would sort of tell a story almost in video form. That's in fact how today's modern videos work, and really films back in the day, whereby you're just seeing a whole bunch of frames, a whole bunch of pictures again and again, maybe 24 of them per second, maybe 30 of them per second. Nowadays, maybe 60 of those frames per second, which is technically still just a sequence of images. But you and I and our eyes and brains perceive it really as fluid motion. And back in the day, these things were indeed called motion pictures. They're still just pictures flying across the screen, but creating, of course, the illusion of motion to our own eyes. And so indeed, you might think in simplest form of a video as just being 30 images, 60 images, thousands of images, each on the screen for a split second, but each of those images composed of thousands, if not millions of pixels, and therefore amounts of red, green, and blue. Now, as an aside, there are many different ways to represent images and videos. There are different formats that use different mathematics to gain efficiency. So you don't have to literally store every frame from a movie as an outright picture. But in simplest form and for some file formats, this is literally how it's implemented. And indeed, at the end of the day, like I proposed before, if we only have zeros and ones, this is the only possible way, really, that we can represent even more sophisticated things, because our vocabulary ultimately consists solely of those zeros and ones. Now, videos often have music, and music certainly can stand alone. How might we represent musical notes? Well, here too, there's a bunch of different ways in the real world, but in simplest form, I think we just need to agree as a society what number represents the musical note A, and B, and C. What number represents a sharp or a flat? Now, the pitch of the note is maybe not sufficient, so maybe we don't just need one number per note. We should probably use a second number, maybe a second byte, to represent the volume of a note, like how hard you're hitting the physical keyboard in order to make that sound. And maybe just the pitch and the volume aren't quite enough to express music, certainly the most melodic of music. Maybe we instead also need a third number to represent the duration of each note, like how long my finger is on the key on the keyboard. So with those three numbers, I dare say, we could probably play a little tune like this simply by teaching the computer, programming it, if you will, what pitch to play based on the numbers it's seeing inside of the file or the music that you've somehow downloaded. So at this point, allow me to stipulate that we clearly have ways of representing information. At the end of the day, today's computers typically use binary, zeros and ones. And at the end of the day, we're leveraging electricity and tiny little switches to turn things on and off and to store patterns of zeros and ones. In simplest form, to recap, those zeros and ones can represent numbers. That was pretty straightforward once at least you knew what base you were using. We can even represent letters, so long as the world sort of comes together in an agreement as to what numbers represent what letters. And we can represent colors if we do the same. We can represent videos if we do the same. We can represent music if we do the same. But there too, to my comment earlier about file formats, among the reasons we have so many different file formats for documents, for images, for videos, for music, is because reasonable people will disagree. And different people, different companies, different organizations will decide, no, our representation of this information is better than someone else's. Therefore, you should use our file format and not someone else's. Nowadays, of course, most any program you use can often, when you go to the File menu and Open, can often open different file formats. And that's in the interest of compatibility. But at the end of the day, what a file is on your computer or on your phone is just a whole bunch of zeros and ones stored somehow electronically. And inside of those zeros and ones are patterns that represent maybe numbers, maybe letters, maybe colors, maybe images, maybe music, maybe video. But depending on what program you're using, those same patterns might be interpreted differently. And in fact, as per our example with 72, 73, 33, you might perceive that as numbers if you open a file containing those 24 bits in a spreadsheet program like Microsoft Excel. You might see letters of the alphabet, though, if you try to open that same pattern of 24 bits using something like Microsoft Word. You might see something different if you open that same pattern of 24 bits using Photoshop or QuickTime Player or any number of other pieces of software. And in practice, you're not going to open such tiny files that they only contain 24 bits. Odds are they'll contain thousands of bits, millions of bits, billions of bits. But the context matters when viewing those zeros and ones. And indeed, at the end of the day, it's all zeros and ones, but you see and perceive and hear differently based on what software you're using. And some human, some company has written that software to support those particular patterns of zeros and ones. All right. So again, let me stipulate that we have a way to represent information as per the low-level details that we've talked about here to a higher level, from bits all the way up to now video and music. Let's now focus on this proverbial black box. When it comes to solving problems and computer science more broadly, we can now represent our inputs in some way using binary or whatever. We can represent our outputs in that same way. how do we actually convert our inputs to outputs? Well, for this, in the world of computer science and problem solving more broadly, we need what we'd call algorithms. Algorithms is a phrase that's sort of everywhere these days in computing. It's really just step-by-step instructions for solving some problem. And those step-by-step instructions can be in English or any human language. It could be implemented in code instead, whether it's in languages like C, C++, Java, JavaScript, or any number of other programming languages that we'll touch on in some detail later in the course. And indeed, code is just an implementation of an algorithm in a way that a computer can understand. And one such algorithm might be looking someone up in a phone book. In fact, here is an icon that I might have on my phone. And if I tap on that icon, I see all of my contacts, my address book, all of my family and friends and colleagues' names, numbers, and nowadays email addresses and home addresses and other information as well. But it's really just a collection of minimally names and, say, numbers for the sake of discussion. In fact, it's really just a modern incarnation of this here old technology, namely a phone book. And in fact, I tried to find the biggest phone book I could, but they're getting smaller and they're getting a lot harder to find. But back in the day, around the time I was sitting under the warmth of that RGB projector, this was the technology we had for looking up names and in turn numbers. We had the people whose names started with A at the beginning of this here phone book, people whose names started with Z at the end of this phone book, which is sort of obvious as that might be now, is exactly how our phones are implemented as well. But the numbers and the names are stored instead using zeros and ones underneath the computer or the hood of the phone. All right, so with that said, how might we look someone up? For instance, John Harvard, if I were to tap on his name in my phone or search via autocomplete, I might see something like this, like his your phone number. In fact, you're welcome to call or even text message John at this here number. If, though, I wanted to find John Harvard in this phone book, how would I go about that? And in turn, how does my phone actually go about finding John Harvard the same? Because it's so darn fast in a phone nowadays, whether you have tens of friends and family or hundreds or thousands, it's pretty darn fast, today's autocomplete. But it turns out it's probably not doing it in the most obvious, simplistic way. You could certainly imagine starting at the A names, looking at the B's, the C's, the D's, all the way down to the J's for John Harvard, if at least it's sorted by first name instead of last, for the sake of discussion. And I could actually take that approach with this here physical phone book. Here's my algorithm. Step by step, I'm going to look at the first page, look for John Harvard. If I don't see him, I'm going to turn the page. I'm going to repeat. I'm going to repeat. I'm going to repeat. So if this phone book here has maybe like 1,000 very thin pages, it might take me, in the worst case, 1,000 page turns to find John Harvard. But I do dare say that this algorithm, this step-by-step process for solving this problem, is indeed correct. It's sort of stupidly slow because I'm nowhere close to John Harvard yet, even though I've turned all of these pages. But it is correct because so long as I pay attention and look for John Harvard on each page, if he's here, I will find him, if slowly. All right, well, what could I do that's a little more intelligent and a little more efficient than that? Well, I could start the same way, but I might go 2, 4, 6, 8, 10, 12, and so forth. I could go 2 pages at a time. Now, is that algorithm step-by-step correct? Not really, because I could get unlucky. And at some point, John Harvard might very well be sandwiched between 2 pages. And I'm just going to blow past that and miss him. Now, do I have to throw out that algorithm? Because I was kind of liking the sound of it. It's 2, 4, 6, 8. I mean, it literally is and sounds twice as fast. But I don't have to throw out that algorithm entirely. Why don't I just look down? And if I ever get past the J section, thus having passed John Harvard, alphabetically sorted by first name in this story, I can just go back 1 page, because if he was, in fact, sandwiched between, OK, fine. It's twice as fast plus 1 extra step. And if this phone book has 1,000 pages, that first algorithm could take me as many as 1,000 steps. But the second algorithm might take me 500 steps, OK, maybe 501 steps if I have to double back as soon as I pass him. That's pretty darn good, that second algorithm. That's twice as fast, give or take. But that's probably not what our phone is doing to search larger and larger sets of data. That's not even what you and I probably did back in the day, or mom and dad, or grandpa and grandma, or beyond. What instead we probably did was open the phone book roughly to the middle here. And of course, if I'm looking down at the middle of the phone book, I'm not going to see John Harvard most likely. I'm going to see like the M section, at which point I realize, darn it, I've gone too far. But what do I know about John Harvard's position in this here phone book? Well, here's what I'm seeing. And John Harvard at this point is where? To the left or to the right? John starting with J. It's clearly to the left if I've opened to the M section. And so what I can do here is actually literally and figuratively tear this problem in half, throw half of the problem away that does not contain John Harvard, because I know that the J names are in this half. Now, what's compelling about this, if unnecessarily dramatic, is that I've whittled down a 1,000-page problem in just one step to 500 pages. Now, I might open roughly to the middle of this remaining phone book, and I went too far. Now I'm in, say, the E section of names. But I now know that John Harvard, if these are the E's, is to the right. So I can again tear this problem partially away and again in half, throwing now this half away, A through E, because I know John Harvard starting with J must be in this portion of the book. And I can do that again. I can do that again. I can do that again, dividing and conquering, so to speak, until John Harvard is hopefully on the one and final page that I've torn that phone book into. Now, this is not actually how we used phone books back in the day. And in fact, this is why they're so hard to find, because we keep doing this with them. But this phone book does represent how we might solve a problem more efficiently by using the third and final algorithm instead of those first two. Why? Well, in the first case, again, if we're searching for someone, maybe their name doesn't start with J, it starts with Z at the end of the English alphabet. Might take as many as 1,000 steps to get to the 1,000th page in the book. Well, the second algorithm might take 500 steps, plus 1, 501 steps, which is much faster. But what about this third and final algorithm where I divided and conquered again and again and again? There's actually a binary aspect to that in that I'm tearing the phone book in half, in half, in half. That is to say, how many times can you tear a 1,000-page phone book in half? Well, if you do it once, you go from 1,000 to 500. If you do it again, you go to 250. Again, 125. Again, you have to start rounding, but we can come up with a solution to that problem. How many times until you get to just one page remaining? Starting with 1,000 pages, it's roughly 10 steps total, depending on how you round along the way. 10 steps instead of 501, instead of 1,000. That is an order of magnitude faster, so to speak, than either of those first two algorithms. And that's, in fact, exactly what Google and Apple and others have implemented in your phones and our laptops and our desktops to search not just address books like these, but large amounts of information more generally. And in fact, there are even more sophisticated algorithms out there, step-by-step instructions for solving other problems that are even faster and more sophisticated than these, perhaps. So once we have John Harvard, and quite quickly too, how can we think about how much faster that was? I rattled off some numbers here, but let's see if we can appreciate the implications of this longer term. So here's a very abstract picture of math, if you will, where I've got an xy plane, where on the x-axis I've got the size of the problem. So over here would mean small problem. Over here would mean big problem, so to speak. Down here on the y-axis would be little time to solve. Up here on the y-axis would be a lot of time to solve. So how could we plot the relationship between the size of the problem and the time required to solve that problem in the context of this here phone book? Well, here is a slope of n, if you will. N just representing a number. And in fact, that's the go-to variable name, if you will, for many computer scientists when they just need a number, like n here. And so that's a one-to-one relationship. Why? Because if someone moves to town next year, that phone book is going to have one more name in it. Or if a bunch of people move to town, it's going to have one more page, one more page, one more page. So there's a one-to-one relationship, if you will, between the size of the problem and the amount of time it might take to solve, because one more page means I might have to turn one more page using that first algorithm, step by step by step, one page at a time. The second algorithm was in fact faster, but it's still actually a straight line, because it might take me roughly n divided by 2 steps. It might not be exactly n divided by 2 in the worst case, but because I might have to double back that one page at least, but it's still a straight line. Because if the phone book maybe doubles in size next year, it's going to take me not twice as many steps, but 50% more steps. That's not the right way to say that. Damn it. Sorry. It's still a straight. Let's do it from here. It's still a straight line, but the slope is now n divided by 2 because I was going 2 pages at a time. Now, it might not be precisely n divided by 2 because I might have to double back that one page, but it's indeed still a straight line because there's a 1-to-2 relationship now between the number of pages therein and how quickly I'm going. I don't like that either. Sorry. Slope of OK. Now, this, did I say the slope of the line is n?
I don't recall that verbiage per se.
All right. I don't think so. But I was coming dangerously close to that with the yellow line. Now, the second algorithm might be represented with this yellow line here, which is still a straight line, but it does capture the fact that that algorithm was faster. Why? Well, let's consider some specific size of problem. So if we have 1,000 pages, maybe represented here with this dotted line, the first algorithm in red is going to take this much time over here. The second algorithm, though, because I was going 2 pages at a time, does strictly take less time. It's going to take this much time, half as much time, give or take, for that doubling back. But the third and final algorithm, whereby I was dividing the phone book in half, and then the half in half, and then the half of the half in half, is fundamentally faster. And if we were to draw a picture of it, it would look a little, something like this. Let me fix that again. I forgot about this line here. Sorry. Now, the second algorithm is still a straight line, but it is ultimately faster than the first algorithm as follows. Notice here that if we pick a size of the problem, for instance, if this line here represents 1,000 pages here in dots, well, the first algorithm, wherein I was going 1 page at a time, would take this much time, be it in pages or seconds or minutes or whatever our unit of measure is. But the second algorithm might only take this many steps, roughly half, give or take based on whether we have to double back or not. And so the yellow line here, the second algorithm, wherein I went 2 pages at a time, is definitely faster. But that third and final algorithm, whereby I was dividing the phone book in half, and then the half in half, and the half of the half in half, is fundamentally faster. And in fact, if we were to draw the same relationship between size and time, we would actually see this green line represented here as a logarithm. And log base 2 of n is the way that mathematically you could capture the fact that that problem is decaying exponentially. It's going from big to half to half to half to half. That's a much faster solution there, too. And what's powerful about this third and final algorithm is that, notice, even if that phone book gets twice as big, for instance, maybe the towns of Cambridge and Allston in Massachusetts, which Harvard has buildings in both, were to combine their phone books such that one year the phone book has 1,000 pages, and the next year the phone book has 2,000 pages for both towns, well, that's going to put the size of the problem like way out here. But based on the apparent slope of this line, which is no longer a straight line, it's not going to take that much more time, even if the problem is way out here. Why? Because no big deal. If the phone book suddenly has 2,000 pages using that third algorithm, fine, I tear it in half 1 more time, not 500 more times, and certainly not 1,000 more times. And so in computer science, and in the study of algorithms in particular, is thought processes like this. How can we solve our problem not just correctly, but more efficiently? And what makes one company's or one person's algorithm better than another might very well be that a person's algorithm takes less time, or as we'll see, maybe uses less space, or maybe uses some less of some other resource. And in fact, algorithms not only solve problems, but can be compared in this way, even without getting into the weeds of specific numbers, but with broad strokes, if you will. And in fact, this notation, which hints at something called asymptotic notation, is how theoreticians would typically argue that one algorithm is better than, or worse than, or about the same as another algorithm, by really trying to capture how that algorithm behaves, not for small little problems like phone books like these, but when you have millions of pages in the problem, billions, trillions. When n gets large is when algorithms really get interesting. OK, we're almost done. Now, what's the connection between these algorithms and maybe the code that software engineers and sorry. Now, what's the connection between these algorithms and the programs that software engineers write? Well, last time. Falling off the horse there. Now, what's the connection between algorithms in this theoretical sense and the very practical work that a programmer does? Well, code, be it written in C, C++, Java, JavaScript, or any number of other languages in the real world, is just a translation of algorithms, again, to code, or in turn language that the computer itself understands. Because until we had AI, computers didn't really understand English per se, certainly not to the extent that they suddenly seem to. Let's not do that. It's getting too current. One more time. Now, what's the connection between these algorithms and the programs that people write? Well, sorry. Okay. Now, why is computer science and with it algorithms so intertwined with programming and software engineering in the real world? Well, code that programmers write is really just a translation of algorithms into a language that a computer itself understands. And that language might be C or C++, Java, JavaScript, or any number of other languages as well. But for today, let's give you a taste of code in the sense of pseudocode, which has no formal definition, but which is just a terse, succinct way of expressing your thoughts step by step in the form of an algorithm using English or whatever your human language is. That is to say, when writing pseudocode, there's no one way to write it, but it's meant to be succinct and terse, but ideally as precise as possible nonetheless. So for instance, what might have been the pseudocode via which I was searching for John Harvard in that phone book using the third and final algorithm? Put another way, if I wanted to tell someone else how to do exactly that algorithm, or tell a robot to do just that, or to write software that my phone could understand like Google and Apple, how could I translate my idea, that algorithm, into step-by-step instructions? Well, I could do this any number of ways, but let me propose that the first thing I did with that phone book was I picked it up. The second thing I did was I opened to the middle of the phone book. The next thing I did was looked at a page, and then I asked myself a question. If the person I'm looking for, John Harvard, for instance, is on the page, then I did something specific, I would have called that person. Of course, in my exercise, I didn't find John Harvard first. I kept looking, so I might have asked myself another question. Else, if person is earlier in the book, to the left, so to speak, then I didn't try to calling them yet. Instead, I opened to the middle of the left half of the book. But if that wasn't the case either, and, oh, damn it. And then, how can we fix this? Just look up. OK. I would open to the middle of the left half of the phone book. And then I could go back to step 3. Sorry. Open to the middle of the left half of the book. And then I could go back to line 3. Why? Because in line 3, I'm already have instructions via which to look for John now that I have open to the middle of the left half of the book. But suppose that John weren't, in fact, to the left, but the person I'm looking for is to the right later in the book. Well, then I would do almost the same. I would open to the middle of the right half of the book, and then I would go back to line 3, because line 3 would get me ready to look for John or anyone else step by step again. But there's a fourth and final scenario to consider. If John is not on the page, or earlier, or later, because maybe I've divided the thing in half so many times that I'm at the last page and he's not there, there's a fourth and final scenario, which I dare say should be else just go ahead and quit. Because if he's not there, or to the left, or to the right, logically, it must be the case that John Harvard is not there, so I'd better handle that situation step by step too. And this is actually a key detail. Even though this is pseudocode for a very real-world algorithm or process, it turns out that forgetting about or not realizing that some other scenario could happen is a common source for today's problems in software. In fact, if your own Mac or PC or phone has ever frozen, or maybe a spinning beach ball persists forever, or maybe it reboots or turns off entirely, it's possible that that is the result of some human at whatever company wrote that software having forgotten, oh my gosh, what if the person is not even in the phone book? We'd better tell the device what to do in that case. Because if you don't tell the device what to do step by step, maybe the behavior is just undetermined, and so it freezes, it hangs, it reboots, because it doesn't know what else to do because you have not told it the correct step. So if we assume now that this is complete, let's see if we can't glean some first principles here and some terminology as well, via which we can solve not just this problem, but others as well. There are some key characteristics of how I've written my pseudocode here, and in fact, in English specifically, that will guide our solutions to future problems as well, whether it's in English or actual code. For instance, notice that in some of these lines here, there are verbs or calls to action, if you will. Pick up, open to, look at, call, open to, and quit. Well, those verbs in the world of computing have a term of art associated with them, namely functions, borrowed from mathematics, whereby a function is an action or verb that tells you or the robot or the computer to do something specific. So any of these actions can be now described in the world of computing as functions herein. These terms here, if, else if, else if, else, represent what a computer scientist and any programmer would call a conditional. These are forks in the road, so to speak, that you take only based on the answer to some question. You either go this way, or this way, or this way, or this way, if it's a multiple directions you can go, based on the answer to some question. For instance, if the person is on the page, or the person is earlier in the book, or the person is later in the book, you will decide whether to go here, 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 or here instead. Else, as is the semantics, means sort of a catch-all. If none of the answers to those questions are yes or true, so to speak, at least there's that fourth and final catch-all that just says quit. But these highlighted expressions, these questions to which the answers must be yes or no, or true or false, or heck, 1 or 0, if you will, are generally known as Boolean expressions, named after mathematician Boole. And a Boolean expression has just that, an answer that is either true or false, yes or no, or the like. And so using these building blocks, can we capture my step-by-step logic? But recall that I also had some savings whereby this algorithm didn't keep looking for John, keep looking for John, keep looking for John by having dozens or hundreds of lines. Rather, I told myself in some cases to go back to another line so that I could reuse code that I had already written. And this, too, is a key principle of computing, is to not repeat yourself, ideally keeping things simple so that you don't have to enumerate again and again and again, turn the page, go left, go right. You can say it once and then reuse, so to speak, the code that you've already written. And so highlighted here are what we might call in computing loops. A way of inducing some kind of cycle that hopefully is not infinite. Hopefully, eventually, we stop doing this. Otherwise, you might get the equivalent of a spinning beach ball. But rather, in this case, I don't think we will, because on every iteration of this loop, if you will, I am presumably calling the person or quitting or dividing the problem in half. So even though I might do this again and again and again, and each of those iterations up till the last, I'm making the problem smaller and smaller and smaller. And ultimately, that person's either going to be on the page or I can simply quit. Now, as an aside, sometimes infinite loops are good. Your phone, your computer typically has a clock that you can look at, the current time. Hopefully, the clock is implemented with some kind of infinite loop so that it always tells you the time and doesn't just stop when the clock strikes midnight. It loops back around and does it again. So infinite loops can be good, can be bad. But loops are one construct that we can leverage when translating algorithms into actual code, or in this case, pseudocode. Functions are the actions we can take. Conditionals can guide which direction we go. And the Boolean expressions is how we might decide which path to take when we encounter that fork in the road. So along this path, then, we've come up with a way to represent information. Along this path, we've come up with a way of processing information, looking up John Harvard. And indeed, in the lectures to come, we'll begin to build upon these building blocks, these first principles, if you will, spending not much time at all on binary and zeros or ones anymore. Because, in fact, after today, we can really abstract on top of that low-level detail. We can assume that all of us know that, even if we get rusty eventually on how it's done, that computers can represent not just numbers, but letters and colors and images and videos and music and more. And so as we proceed in the course, we'll build upon this knowledge so that in the real world, can you encounter not only problems like these, but yet others using the same first principles to solve the very new. We'll see you next time. So we now have a way to represent information. We've seen ways via which we can process information, but these are techniques now that we'll mostly take for granted. Indeed, per the top of the class, we'll begin to abstract. Let's fix that again. Sorry. So we now have ways to represent information. We now have ways to process information. And I dare say we can now take for granted that we can do both of those. In fact, here on out, in the lectures to come, we're going to take for granted that we can represent letters, and we can represent images and videos and music and more simply by abstracting on top of these underlying implementation details. And indeed, among our goals for the coming weeks, using first principles as to how systems work, we'll be able to reason through new problems that we encounter that might very well be similar to past problems, but themselves new, so that we can apply these lessons learned to all problems, technical and non, using such and this is just words now. One sec. I might have to stick with the first. OK. So we now have ways to represent information. We now have ways to process information. And moving forward, I dare say we can take for granted that we can do both of those. In fact, after this lecture, we're not going to talk about binary all that much. We're going to take for granted that computers do store information using zeros and ones. We're going to take for granted that we can agree on a system to represent letters and colors and images and videos and music and more. But we can abstract away from those implementation details so that we can solve problems of greater interest to us. In fact, among the goals for studying these first principles of computing is that when we encounter a problem in the real world, be it in or outside of computer science, we can apply some of these lessons learned to familiar and unfamiliar problems alike. And indeed, at the end of the day, I dare say that's the value of computer science, is the applicability of these ideas and these skills to other domains, so that even if you are not a computer person yourself, you can bring to bear lessons learned from classes like these to the world of the sciences, so close. Last time. Should have just stuck the landing and kept. Here we go. OK, Max? So we now have a way to.
Wait a second. We just want to make sure we continue.
OK.
Just 1, 2 seconds. Advance to the next slide. Take a step forward, like you're just covering up the TV a little bit. So take a step forward. One more. I think that's good.
Just as well that none of the other takes were good.
All right. And one more.
So we now have a way to represent information. We now have a way to process information. But here on out, I think we're going to take for granted that we can do both of those. In fact, we're not going to talk very frequently about how we can store information in binary. We're going to take for granted that computers can do so. And we're going to abstract away from that implementation detail. OK, let's go with the first take, which was much better.
OK.
Yes? Was the first time OK? Actually, yeah, let's try this once more, because there's one point, sorry, that I think.
I was going to say, it seems like you have more you want to say at the end, which is why we're doing this.
Yeah. All right, let's try once more. Ready, Max?
Yeah.
So we now have ways to represent information. We now have ways to process information. But I dare say here on out, we can sort of take for granted that we can store information and process information in these ways. In fact, we'll take for granted. I lost my flow. One last time.
On you.
So we now have ways to represent information. We now have ways to process information. And I think we're now going to abstract on top of those primitives. In fact, we'll take for granted that the computers can store information in binary. And on top of that, we can represent letters and colors and images and videos and music and more, so that we can begin to solve quite quickly higher level problems, if you will. And those problems themselves won't always be in computer science itself. In fact, I dare say the value of computer science is its applicability to fields beyond. So whether you intend to bring to bear the lessons learned of this class to the arts, humanities, social sciences, sciences, physical sciences, natural sciences, or beyond, you'll have an opportunity. I know, that was good. OK, I got to keep it shorter. OK, here we go. So we now have ways to represent information. We have ways to process information. So I think we can take for granted that we can do both. In fact, we're not going to talk about the lower level details of binary here on out all that often. We're just going to stipulate that computers can do so. And we're going to take for granted that we can abstract our way on top of those zeros and ones to represent things like letters and colors and images and videos and music and more. And ultimately use some of these first principles to solve higher level problems of interest to us. And those problems don't have to be within computer science. Indeed, odds are you yourself come from the arts, humanities, social sciences, natural sciences, or beyond. And what's nice about computer science is its sheer applicability to those and other fields. In fact, the lessons learned from classes like these should empower you to bring to bear the principles of and the skills from computer science to solve problems of interest to you in your own domain. So all that and more, we'll see you next time. That was good. Can we make note to keep that one or the first one?
Yep.
Thank you all.
Can you write it down?
Oh, yes. For those of you still with us, thank you so much, and especially thank you for bearing with me as I went off the rails there at the end. This was the first of our live streams again for the new and improved version of CS50 Business to be retitled. We'll be back tomorrow at 9 a.m. Eastern time for Colton's third lecture for CS50 2D, the two-dimensional gaming course. If you'd like to find the Zoom and YouTube URLs for those, head to cs50.ly/Zoom. Hope you can join us for those as well as next week's lectures as well. See you soon.